Hello viewers, welcome back to Coding Interviews channel. Hope you're doing great. If you haven't subscribed to the channel yet, please go ahead and subscribe. I have created a bunch of playlists to cover various categories of problems such as BFS, DFS, dynamic programming, stacks, queues, linked lists, trees, graph, and so on. Please check them out. I have uploaded the code for this particular problem to the GitHub repository. You can get the link from description below this video. Let's jump into today's problem. Unique binary search trees. Given n, how many structurally unique BSTs that store values 1 to n? So basically we are given with a number n, okay, and the values are starting from 1 till n, right? So now we need to identify how many unique binary search trees structurally possible, right? So basically the binary search tree property, right? So if you go look back the binary search tree property, so the left subtree should be less than root and root should be less than right subtree, right? So this is the simple definition for BST, right? Now we are saying there are n nodes or n elements, we will say, right? N nodes starting from 1 to n, right? So 1 till n. So there are n nodes in the binary tree, right? So when there are n nodes in the binary tree, there could be multiple possibilities that could happen, right? So now we are asked to find out how many structurally unique BSTs, right? So structurally means, so the values probably may be different, but the structure should be unique, right? Like that. So let's go try to understand the process that we are going to get the logic for this particular problem, right? So as we are saying n is the number of nodes in the binary search tree, right? So then obviously when we are talking about binary trees, there will be a left subtree, there will be a right subtree, and there will be a root, right? So by keeping that in mind, right? So if which one is optional in them? Left subtree or right subtree is optional, but root must be there, right? So assuming that there is at least one node, since our numbers are starting with 1, right, I would assume the tree has at least one node in it, right? So if the tree has one node in it, then that will be simply a root node, right? We don't have any further things, right? But if there are n nodes, that means one of them is root node, right? And one of them is root node, and I'm calling there are n minus 1 are remaining, right? So 1 we already allocated to root, so there will be n minus 1 nodes are remaining, right? So now our task is to distribute this n minus 1 nodes into left subtree and right subtree, right? So we could divide this n minus 1 nodes in so many different ways, right? Simply saying n minus 2 different ways, right? So if there are n minus 1 nodes, you could divide them in n minus 2 different ways. So let's see what those ways are, right? So let's say if there is one node in the left subtree out of this n minus 1, right? So how many nodes will be there on the right subtree? N minus 2, right? So this total are n minus 1, right? One is, if we move further, right? So let's say there are two nodes in the left subtree, right? And then there might be, or there can be, n minus 3 nodes in the right subtree, right? So on the whole, if you add the number of nodes in the left and number of nodes in the right, that should be equal to the n minus 1, right? Since we are saying there are n minus 1 nodes remaining after the root node is selected. So n minus 3 plus 2 is n minus 1 again. So going on with the further distribution, right? So if there are 3 nodes, there should be n minus 4 nodes in the right subtree. So on if we go, right, finally what we say is n minus 2 nodes in the left subtree and 1 node in the right subtree, right. So that is possible, but there are two more cases also possible. We started saying, okay, left subtree or right subtree is optional, right. That means what we can say is there can be 0 nodes in the left subtree and all nodes can be, all n minus 1 nodes can be in the right subtree, and the reverse case, basically there are n minus 1 nodes in the left subtree and 0 nodes in the right subtree. So that is also a valid case, right. So if you follow that, right, in the example given on the left side, input is like 3 nodes, right. So for this one as the root, the number of nodes in the left subtree are 0 here, right. If you closely observe, the number of nodes in the left subtree of 1, the node 1 is 0, right. So similarly, the number of nodes, right, here in the right subtree are 0, right. So these are the cases that we are talking about, right. The number of nodes in the left subtree and number of nodes in the right subtree could be 0, right. And now since we are dealing with one node at a time, right, so out of n nodes we picked one node and we distributed the remaining n minus 1 nodes into left and right subtree. Now let's go with this example, right. So let's go with this example, right, further. So there is only one node on the left subtree, so we will not be able to make more than one tree with that, right. So that is constant, but there are n minus 2 nodes on the right subtree. So now we will have to pick one node as the root out of this n minus 2, right, and there will be again distribution going further from the n minus 2 nodes. So once you pick the one node as the root node, how many nodes will be remaining? N minus 3. So now you have to distribute this n minus 3 nodes into left and right subtrees. So this thing will go on and on, right. So when you do this math all together, right, so you see same problem is being solved multiple times, right. So here we picked one root node, right, one root, so n minus 3 remaining, right. So if you look the step below, right, n minus 3 nodes on the right subtree, right, so that this n minus 3 and there is n minus 3 here. So that means we will be doing the similar calculations multiple times in here. So when you have that kind of scenario, right, this is a good case to use a dynamic programming approach, right, so that you don't have to calculate the same thing more and more number of times, right. So we are going to solve this problem through dynamic programming approach, and since we are dealing with, okay, there will be some number of nodes on the left subtree and some number of nodes on the right subtree, and obviously there is one root node, right. So with that we can, if we go further and calculate, right, we will come up saying, okay, for a given number of nodes, the number of binary trees possible are equal to the number of nodes in the left subtree into the number of nodes in the right subtree. That is the thing that we will get at, right. If we go further and dive into all these different options, right, we will end up with this formula. So the number of nodes in the left subtree into the number of nodes in the right subtree for a given n, right. So this is the approach that we are going to use in order to solve this particular problem. So this is one approach, and we will come back for the second approach, okay. So this is first approach we are going to look at the code for, right. So I'm calling this num trees as DP, basically dynamic programming. If the number of nodes is less than or equal to 1, then we are saying, okay, there is only one tree possible, right. So if it is 0 nodes, that empty tree, right, that is structurally unique binary tree, so binary search tree, so it is one tree. If it is n is equal to 1, then also it is one tree possible. So now going on further, what I am going to do is declare an array dp array which is of length equal to n plus 1 and initialize the first two elements. As we are saying, when n is equal to 0, there is only one tree possible, right? When n is equal to 1, there is only one tree possible. Those are the two things which we already know. That is why I am initializing the base cases. Now, starting from 2, right, what I am going to do is, now I need to calculate the number of left subtrees and number of right subtrees, right. So, that depends on how many number of nodes are in the left subtree and how many nodes in the right subtree. So, what we are going to do is, we are going through exactly this kind of distribution, right. So, there is one node on the left, n minus 2 nodes on the right, there is 2 nodes on the left, n minus 3 nodes on the right. So, this is a similar thing that we are going to use, right. So, let us go and look at that. So, we will start with I is equal to 2, right. So, that is, since we already know the answers for when the tree is with 0 nodes and when tree is 1 node. That is the reason why we are starting with when the tree is with 2 nodes, right, and we will go on until the tree has n nodes, right. So, that is what we are going to do now. So, what we are essentially doing is, there are some number of nodes on the left subtree and some number of nodes on the right subtree, right. So, what is that sum number? So, there will be 0 nodes on the left subtree and all n minus 1 nodes on the right subtree, right, and there is one node and n minus 2. So, likewise. So, that is the reason why we have another for loop here, which is going from 1 to I, right. So, if there are 3 nodes, so it will go from 1, 2 and 3, that is how it is. So, on to the left subtree, we are saying there are j minus 1, that means we are subtracting one node as the root node, right. So, that is what we are going to get the value from the dp array, and right subtree the remaining nodes onto the right subtree. So, we are getting the values from left and right, and what we are doing is essentially multiplying the left and right, that is what we are doing, and then storing that value into the dp by adding whatever the number that is available within the dp. What we are essentially doing is the number of subtrees with left subtree and right subtree and multiplying them for that n, right. So, as j moves, we will be doing that many different kinds of trees, and finally, the dp will be filled with the final answer for a given n. So, when we are going to return an output, right, we will be returning the dp of n, right. So, that is the simple way of coding this dynamic programming approach. Let us look at the time and space complexity for this. So, time, space, right. So, what is the time complexity? Assuming that there are n nodes, right. So, this outer loop is going through n minus 2 times, right. So, n minus 2, right, and the inner loop is going from 1 to I, right. So, typically what we say is, this is when I is equal to n, right, it is going from 1 to n, right. So, we will say the time complexity for this particular algorithm will be order of n square, right, n square, right, that is what we will call. Let me put another bracket right here, so that it is easy to understand, right. So, that is what the time complexity. And what is the space complexity? So, the space that we are using is the dp array, which is equal to n plus 1. So, let us say order of n plus 1. So, are we using any more space? Not really, right. So, in that particular case, the space complexity will be order of n plus 1, but since we are going to remove the constants from the big O notation, it will be order of n, right. So, time complexity is order of n square and space complexity is order of n. So, now let us go with the second approach, right. So, approach 2, right. So, in this approach, what we are going to do is, instead of going through the formula, instead of going through all the formula that we came up, the left subtree into right subtree, right. So, there is a formula that is derived out of this. So if you keep on doing this number, right? So if you keep on doing this, the going through the 2 for loops and adding all these numbers and all, right? So there is a number mathematically that we will be able to get it, right? So there is a formula directly that you can get for a given n, how many unique binary search trees are possible, right? So that is called combinations. So it's based on the combinations. Okay, so it's simply how you have to understand is we are saying if there are n nodes, right, combination of n nodes, right. So that means we will say, okay, combination of 0 nodes in the left subtree and combination of n minus 1 nodes, right, plus combination of 1 into combination of n minus 2, right. So that is what we are going to have until combination of n minus 1 into combination of 0, right. So this is what we have been doing as part of these two for loops, right. So 0 nodes, n minus 1 nodes, 1 node, n minus 2 nodes, like that, right. So these are all we are adding them. That is what is C of n, right. So mathematically, if you solve this equation, right, it will come up as 2n combination of n, right, by n plus 1, right, 2n Cn by n plus 1, right. So this is a combination. So in other words, we can write like this also, this one, right, C of 2n comma n by n plus 1, right. So this is the answer for this complete equation is this combination of 2n Cn by n plus 1. So if you know what is the formula for NCR, right. So if this makes real sense for people, right, NCR, right. So which is equal to n factorial, right, n factorial by r factorial into n minus r factorial, right. So that is what is the formula. Okay. So NCR. So now we are going to write this 2NCn by n plus 1 in this format, right. So by following this formula, what it becomes, n is here 2n, r is n, right. So there is n plus 1 anyway that we need to put. So in place of n there is 2n, right. So that means what it will become is 2n factorial, right, 2n factorial by r factorial is what, r is what, n, right, n. So n factorial into n minus r, what is n, 2n, r is what, n, 2n minus n is n. So n factorial, one more time n factorial it will become, and there is a by n plus 1, right, here. So into n plus 1, right. So this whole thing will be under this as a denominator. So this is the formula, right, that we will end up with. This is approach 2. So now what we are going to do is simply substitute n in here and get the answer. That's it. So let's go look at that approach. So since we have to calculate the factorial, right, I wrote a private method to calculate the factorial for a given number, right. So it takes n and then calculate the factorial and returns the product. So just by following this, right, so here I need to calculate the 2n factorial first and n factorial. So if I calculate these two, so that is what I am doing here, 2n factorial and factorial I am doing, and then returning that thing, 2n factorial by n factorial into n plus 1, that is what I am returning. So this is a simple approach, right. So this one, if we go look at the time and space complexity, right, so we will say, okay, all we are doing is, okay, taking n and doing the factorial calculation for 2n and factorial calculation for n, right. So, that means we will be going through the factorial calculation of 2n. How much time we will be taking here for factorial calculation of factor 2n? It will be order of 2n, right, order of 2n plus. So, just to remind you, I am calculating the time complexity, right, order of 2n plus what is the time it will take for factorial of n? Order of n, right. So, that will be order of 3n. Since we are going to remove the constants from big O notation, it will be order of n, right, time. And what is the space? Are we using any extra space here? No, apart from these two couple of variables, we are not using any more space. So, that means we will say, okay, the space complexity is order of 1, right. So, in this particular case, what we are saying is we have time complexity of order of n and space complexity is order of 1, right. So, if you compare the two approaches, there is a improvement of order of n in terms of the time complexity and also order of n in terms of the space complexity, right. So, if you have any further questions, please post them in the comment section below this video. I will get back to you as soon as I can. I have posted this code to the GitHub repository. You can get the link in the description below this video. If you haven't subscribed to the channel yet, please go ahead and subscribe and share among your friends. Please click on the bell icon so that you will be notified about all my future videos. Thank you for watching. I will be back with another problem very soon. Till then, stay safe and goodbye.